Good morning, Astronomy 1020. Welcome to part 2 of our 10th lecture. At this point, having watched a couple of pre-recorded videos the last couple of classes, you should have learned about the spectral types of stars. You should have learned about binary stars. And I'm hoping, I'm going to start by asking you guys a couple of questions. It's okay if you use your notes, but I'm just trying to figure out what you know. Like, what did you learn from the videos? I'm sure it's tempting to skip parts and to jump around a bit, but I need to know how much you know before I can talk to you. So let's say I start here with, what are the 4 basic properties of a star that we would like to know if we want to understand the physics of a star? Stars have 4 fundamental properties. Can anyone tell me what they are?
Mass, temperature, luminosity, and there's a 4th one that I don't remember.
Okay, so you know what I'm talking about, though. That's good. What's the 4th one? Who can help Mateus? That's pretty good, Mateus. I was expecting everyone to, you know what I was expecting you to answer? I was expecting you to answer, okay, so you've already done good. You've gotten 3 out of the 4. That's better than I thought. I can't find my black marker, so I'm just going to take a fresh one, I guess. C'est la vie. Okay, so let's just do some quick review notes so that I know you guys know what you should know. So the 4 fundamental properties of a star. Let me go full screen so you guys can see what I'm up to here. Are, of course, the mass, the luminosity, the 4th one that you were looking for, Mateus, is the radius, and then the temperature. MLRT. If you want to know how stars work, you have to know the mass, the luminosity, the temperature, and the radius. These are the sort of 4 properties that govern the physics of a star. Now, I suppose if you were going to be a pesky student, or if you were going to be a skeptical student, you could rightly say to me, well, look, bro, I'm an art major. Why do I want to know about stars? Maybe because you're just curious about nature and you think nature is beautiful. Also, it turns out that if you learn a whole bunch of things about stars, then you end up later on being able to understand pictures like, let's just look at NGC 1300. The goal that we're trying to build up to is for us to know enough about stars that when we look at a totally badass picture of space, like this famous barred spiral galaxy, NGC 1300, we will understand what's going on here. Clearly, you would have to be a truly cynical and boring person to think that this is not a totally beautiful and badass picture of space. But maybe you'd like to know more about it. How big is it? Where did it come from? What's it doing? What's all the colors about? Then you have to learn some basic properties of stars. So there is a payoff, if you ask me, when you can look at a beautiful picture of space and just even have a little glimpse of an understanding into what's going on. Let's talk about how we find these properties, because these properties have to, Jesus doesn't beam the information into our heads, or neither does any other deity like Odin, okay? We have to become astronomers. We have to become observational astronomers and look through our telescopes out into space, and looking at these pretty pictures of stars, we have to try to make some sense of it all. Let's see what you remember. How do we figure out the masses of stars? How do we learn the masses of stars? We can't exactly weigh them on a balance beam.
So you have to use MK3 itself for mass, or you can use the kitty version.
Oh, so you guys learned about the kitty version. That's very, very important.
Yeah, in the previous video.
Okay, so basically, but you're missing the point. In a way, you are right. NK3 gives us the masses of the stars. But the only way you can use NK3 is if you can see 2 things orbiting around each other. And since the planets are too dim, tiny, and faint to be seen, we can only determine masses when stars come in binary pairs. So through the study of binaries is how we get masses. And yes, if you want to look at it one level below that, you get the mass from NK3. But that's like the analysis. The concept is from binary stars. Let's talk about these three things. These three things are related by a famous formula called the Stefan-Boltzmann law for stars. Did you learn this in one of my previous videos? Could someone fire off what it is? You guys are impressing me. I'm actually feeling pretty good about this whole thing.
L equals 4. Well, is it? No, it's the other one. It's R equals the.
No, let's do it. I like doing the L version.
All right. So 4 pi r squared times, what is that constant? What's the name of it again?
Sigma is the name of the. Sigma is the name of the letter, but it's the Stefan-Boltzmann constant. Usually an astronomer would just say sigma t to the 4th.
All right, that's it.
And remember, most of this time when astronomers are talking to each other, they kind of ignore the 4 and the pi and the sigma because those are just numbers that don't change. And the real takeaway from this formula is supposed to be that the luminosity of a star goes as r squared times t to the 4th. And the point is that there's kind of a complicated relationship between the amount of light a star puts out, how big and fat the star is, and how hot the star is. Hotter stars emit more light, but fatter stars also emit more light too, because they have more surface area. This is one of the reasons why Betelgeuse is so brilliant in the upper shoulder of Orion, not because it's the hottest star. In fact, it's quite cool. Betelgeuse is so bright on your sky because it's freaking huge in volume. It's literally the size of your solar system as a star. Okay, on to, you guys have done great so far. Very impressed. Now tell me about the last thing I need to know. Directly determining the radius and the luminosity are complicated, but there is a way to measure the temperature. How can we measure the temperatures of stars?
Types by analyzing their light, their absorption spectra.
Yes, by measuring the absorption spectrum. You guys are impressing me over and over again. So the temperature, we get this from measuring their absorption spectrum. And the absorption spectrum lets us categorize them into a number of different spectral types. And if you remember the Harvard computers, if you remember that, I think that's a funny and interesting story. The story of the Harvard computers in learning to classify the absorption spectrum is how an astronomer determines a star's spectral types. And you guys should know the letters that we classify them into, correct? What are the different spectral types of stars?
Is it O, B, A, F, G, K, M?
Yes. Making me very happy here. Here's a good rule of thumb when remembering the spectral types of stars and their temperatures. An O star, O-type stars, is this a good blue marker? Yes. They usually clock in around 30,000 kelvins in terms of their surface temperatures. These are numbers that
aren't they blue too?
And that's why you, yes, Andrew, and that's why you see me using these symbolic colors. The M stars kind of clock in around 3,000 Kelvin.
3,000.
This is
and
nice.
then the G 6,000.
Ah, yes. Okay. Wow. You guys are making me very, very. I was just like, no one's actually going to watch the videos, but some of you did watch the videos. You're making me very happy. You're making me very, very happy. Now we can have a nice, intelligent conversation. And so these numbers seem easy for me to remember because it's a factor of 10 apart. So it's 3,000 and 30,000. Red stars, whites, greenish stars, and blue stars. Okay. Great. Okay. In that case, I don't know how far the videos went, but it's time for us to learn about how stars form in the interstellar medium. Have we done that, or is it time for us to do this?
Yeah, I don't remember us doing it. No.
Cool. Now, in the book does this kind of weird. They don't really introduce the interstellar medium until chapter 20 when they discuss the Milky Way galaxy. But the idea is that chapter 16 in the book is supposed to be about the birth of stars. I really can't fathom how anyone would talk about the birth of stars without talking about the primordial goo from which stars form, the interstellar medium. And I think there are some interesting aspects of the gas. Is gas in outer space boring, or is it cool? Well, I would like to suggest to you, let's take a trip to the Eagle Nebula. I would like to suggest to you that this stuff is cool. And this is where stars are formed, in the so-called interstellar medium, the gas and the dust that lies between stars and from which stars are formed due to gravitational contractions. Learning about these clouds, you will discover, teaches you a whole lot about where you come from and where the Earth comes from. It's related to why gold is a rare element, or why 2/3 of your body are water, as you will discover in your homeworks today. Okay, so first I want to talk about spectral types and different types of stars. And one thing that we're going to have to understand, we'll take a note on this in a second, is that there's kind of like, even though there are different masses associated with each of these spectral types, there's kind of basically three categories of star: massive stars, little bitty light stars, and then stars that are kind of in the middle. And I'm going to try to give you a sense of what that looks like. If I haven't shown you this picture yet, or this diagram, this illustration is the correct term, let's take a look at it together and let's think a little bit about the big pictures about different types of stars. Have I showed you this picture yet? 74? All right, then this is where we need to be. On the very right, you see what would be considered a very low mass star, okay? This would be like, there's you guys have heard of Alpha Centauri, one of the closest stars to the sun. Alpha Centauri is actually a binary pair, and both Alpha Centauri A and B are like almost identical to our own sun in every way. But what I may not have told you is that Alpha Centauri is actually a trinary star system. It actually consists of two sun mass stars in a close orbit, and then there's a little teensy weensy little dirtbag star named Proxima Centauri. And of course, if you really know your stuff, because Proxima Centauri has a big wide orbit around the other two stars, sometimes Proxima Centauri ends up being closer to the sun than the other two. So at our current epoch, the closest star to the sun is actually Proxima Centauri, not Alpha Centauri, and it's significantly closer. Why didn't I tell you this before? Because sometimes the truth is too complicated. Sometimes you have to tell some lies, okay? So let's take a look at a picture just to inspire you. You would never even know that the three were connected. This is a very illuminating photograph, if you ask me. It's this picture here. Imagine you were looking up at this field of stars. That's maybe Alpha Centauri A, and that's Alpha Centauri B. And do you see in the middle of the red circle that microscopic little red dot? That is Proxima Centauri. You would have no idea that this star was in any way connected to the other two unless you did proper spectroscopic analysis, and you'd have to study their Doppler shift motions too. Usually parallax is how you can tell their distances, right? It took a while for people to figure out that that star is in orbit around the other two. It's not obvious when you're looking at a field of stars. This is one of the complexities of astronomy. Proxima Centauri, can you guys see how much dimmer, how much less luminous it is than the other stars? Keep in mind that all three of these stars are approximately the same distance. And that little red star in the center of the circle is so dim, it's so non-luminous that you can barely see the bugger, right? You can barely see the bugger. And that's because, well, it's because Proxima Centauri is an example of a very low mass star, one that is both cool and dim. Alpha Centauri A and B are examples of stars like our sun. And now I want you to think about a star like Rigel, one of the blue feet of Orion. Rigel is a giant high mass star. And I want you guys now to take a notice that the interiors of the stars are different. And here you've really got to remember your stuff from our chapter on the sun. Let's make sure first that you remember the layers of the sun. What is the outer surface orange layer called? The arrow points toward.
Photosphere.
Sorry?
Photosphere.
That's the photosphere. How about this layer right here? What layer is that?
Middle sphere.
No.
I was just kidding.
The circles should tell you what's up.
Convection zone.
Right. Those little circular arrows that you see are convective bubbles. They're lava lamp bubbles rising and falling. How about this zone in here?
Wouldn't that be the core?
No, the core is the red dot.
Circle, right? All right.
Radiation zone.
That's the radiation zone. What do you see happening in your very low mass star?
Convection.
Yeah, there is no radiation zone. Does that mean anything to you guys? Does that that says something to me. I don't know if you can interpret what that means the exact same. What does it mean that these things have a convection zone that goes all the way down to the core? Actually, the question you should be suddenly asking yourself that you probably forgot is, why does a star switch over from the radiation zone to the convection zone? Why have this transition at all?
So the convection zone is where the cooler plasma goes up and hotter plasma goes down.
Is it plasma though?
Gas.
See,
What?
this is what the difference is between the convection zone and the radiation zone. And it may have been that I didn't emphasize this point enough, because towards the end of the lecture, the class kind of gets tired and I get tired, and then I leave out little details. But here's an important difference. This is a little bit of an aside, but I think it matters since we're going to be talking about stars so much. In the rad zone, the radiation zone, you basically have a fully ionized plasma. So the protons and the electrons are all sort of separated from each other. And when that happens, photons leak through the star by radiative transfer. I'm trying not to use my $10 vocab words on you here, but radiative transfer means light leaking through the plasma. So photons are doing this, and then they bounce off and they go over there, and then they bounce off and they go there, and they bounce off and they go there. In theory, if the star was all plasma, the light would just continue to bounce and ricochet off of the particles. But here's what happens when you get to the convection zone. Suddenly, the temperature barrier drops to the point where atoms start to have their electrons bound once again, and you start having a significant fraction of neutral gas. You know what neutral gas does that plasma cannot do? Absorption. It can absorb photons, and the electrons can eat those photons as they jump from lower to higher levels. Now let's think about what's going to happen. It's as if suddenly the photons hit a brick wall and they start getting absorbed by the neutral atoms. What do the atoms do? They start to form a pocket or a bubble of hot gas and plasma, but mostly gas. And that bubble begins to expand because the photons are just heating up the atoms. And then the bubble begins to rise, and somewhere up at the top of the star, a cool bubble begins to sink. So you see it's the switch from plasma to neutral gas. Now, up to now, I've mostly been lying to, well, I've been telling you the broad picture truth. Do you want to know what the number one, I shouldn't even talk with this. Do you want to know what the number one contribution is to the opacity of the convection zone? It's the H- ion. And this is going to sound fucking crazy. Excuse my French, but the actual contribution to the greatest contribution to the opacity is hydrogen atoms, where temporarily a second electron gets stuck to the atom, and it's the second electron that's super, super, super good at absorbing photons. So I'm kind of telling you the truth, but there's microscopic nuances in there. Anyways, you're going to forget that in 10 seconds, so it's like I never even said it. Okay, now let's look at our picture again, okay? Let's look at our picture again, and let's pretend like we know what we're talking about. What does it mean to us, class, when I see no radiation zone in this low mass star?
Means it's colder?
Yeah, it's so cool that the star is barely even ionized. If the convection zone extends all the way down to the core, this star is literally barely getting it up for fusion, because it only actually becomes a fully ionized plasma right at the very core, where suddenly all of the gas is vaporized into plasma particles, and now you can just barely have fusion. Convection all the way down to the core means these stars are much cooler. And why are they much cooler? Because they're less massive, and it's gravity that squeezes stars, nothing else. Okay, now let's go over to our high mass star and try to figure out what's going on. What do you see here?
I don't see like I don't see a core. Like the previous two stars had this red little core, but this one doesn't.
This, we still consider the center of the star the core, but what do you notice is going on with the core?
The convection is inside, not outside.
Yeah, if I were you guys, that would be very confusing to me. Let's first talk about the outside. This is a radiation zone. What does it mean when you see the radiation zone extending all the way out to the photosphere?
It's extremely luminous. Oh wait, hot.
Well, both, but hot is what I want to say. It's so hot that this star is a fully ionized plasma right from the surface. There's probably no neutral gas in a big fat O or B type star. But how am I supposed to understand the convection?
Is it because of the internal pressure of the star, like from the gravity?
Not just the gravity, but fusion proceeds extremely violently and rapidly inside of a high mass star. And one of the things that we haven't really talked about is what makes there an upper limit to a star? Or maybe I have. Do you guys remember why stars have an upper limit to how massive they can be? Why can't I have a star the size of a galaxy? Shouldn't that be enough gravity to turn on fusion?
Yeah, you said they what is this? Their fusion becomes so intense that they basically, what is this? What did you say? Like blow themselves apart or like fuse
That's
themselves
right.
apart?
Did I show you guys the demo of the light mill, the Crookes radiometer? Maybe it's time for a fun demo, okay? Let's do a little demo together. I have a fun toy that I'd like to show you guys, which will be very illuminating, pun intended. And I actually, this toy is so cool that I sometimes show my friends when they come over to my house. It's called a light mill or a Crookes radiometer, okay? It's a partial vacuum with a very thin needle and a little metallic weather vane on it, okay? Now let's see if I can do this right here. I need to not break this during the demo. That will make me sad.
You broke it in
This
the video.
radiometer costs only $15, so guess what I'm getting next?
This one cost a little more. I made them buy me the expensive one. I can't remember what this was worth, maybe 60 bucks
Oh,
or
wow.
something. But anyways, ordering through the government system is really annoying, Vladimir. So I'm going to try not to break it, but I'll be coming for yours when I do break mine. All right. Here's the conundrum that you have to think about. Light is electromagnetic waves. They are ripples in the electromagnetic field. And because they are related to the force of electromagnetism, they're not supposed to have any mass by definition. Mass is something you associate with gravitational fields, but electromagnetic waves, photons, are massless. This should mean, in theory, that they are not capable of exerting momentum or pressure because, as you learned in an earlier chapter, momentum, the act of transferring some oomph from one particle to another, is mass times velocity. So if photons are just ripples of electromagnetic energy, they should have no mass, and therefore they should have no momentum, and therefore they should have no pressure. And it turns out this is not true, because even though photons don't have mass, they have energy, and energy is kind of like mass, and it's all freaking mixed up together at some level, okay? Let me see if I can flip this computer around. I need to turn the computer around for the demo because of plugs and stuff. So just bear with me here. Hopefully the backlit won't hurt the demonstration. Okay. All right. Nothing incriminating in the photograph. Okay, so here we go. Let's stand this thing up here. Perfect. And let's get it to kind of chill out for a second. It's on a very delicate needle, so. Perfect. Now I'm going to take a floodlight.
Wait, could you focus this a little bit more?
Oh, yes, good call. Good call, Vladimir. Good call. I care about that stuff. I have my Logitech doohickey over here. Good call, buddy. Good call. Spoken like a true astronomer. All right, my cable's not quite long enough. Let's see if I can do this here. Look at that shit. Isn't that insane? I'm literally pushing the weather vane with the power of photons. Light exerts pressure, my friends. You can push things with photons. One day we hope to be able to build spaceships that are like cosmic sailboats that could fly through outer space by being pushed by photons from stars. We could be space pirates, okay, sailing around the galaxy together.
May the force be with you.
May the electromagnetic force be with you in particular. Anyways, the cool point of that demo is that light exerts pressure. Hold on, let me rotate again. Let's get us back here. Careful, 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 careful. Okay. Now, let me show you a cool follow-up picture to that demonstration. Do you want to know what happens to stars that accidentally form with too much mass and too much craziness? Where's my focus? Let me get my focus back under control here. Boom. Stars that form with too much mass, with too much luminosity, they end up suffering the fate of my homeboy, Eta Carina. Eta Carina is a very rare example of a star that we find in the throes, in its death throes, okay? This is what the thing looks like. It's totally awesome. Let's get a couple of different pictures. This one's pretty good. We'll go with this one. This is an example of a star which is literally blowing itself apart due to its own radiation pressure. It's generating so much light at its core, so violently is it generating nuclear fusion and radiation, that the radiation itself is pushing the star apart. And
Oh, so that's the. Oh, sorry.
Yes, this is a star that's exceeded its Eddington luminosity, is the technical term for it. The Eddington luminosity is the luminosity at which the internal photon, not the gas pressure, but the photon pressure itself. You understand that means something totally different, right? It's literally the photons that are blowing the star apart, just like I pushed that weather vane, but at a whole different scale. This star is actually rupturing apart due to photon pressure.
So is this invisible light or some other spectrum?
That's a damn good question. This is a Hubble picture, so this is visible light. There are pictures, they are just processed differently, and that's sometimes, look, you can actually see the diffraction spikes around these stars here and the diffraction circles.
So how fast does that happen? Because like it has to form first, right?
Right.
You can't just
So keep in mind that when you say fast, fast means different things to different people. Fast for a human is not the same thing as fast for a galaxy or a star. Vladimir, you potentially could live to be 100 years old, or maybe even more these days, right? And if you think about it, 100 times 365 days, that means that you have 36,500 days to live your life, if you live to 100. Does that make sense?
yeah.
Let's imagine we took a Polaroid picture of you every single day. We'll have a box full of 36,500 Polaroid pictures, right? If we put that in a box and we shuffled it around like in Powerball, and then we picked a random photograph out, the probability that we would get your birthday when you were born, or the probability that we'd even get the when you were 0 years old or before you were 1 year old, the probability would be pretty low. It'd be 1 part in 100. The time it takes a star like Eta Carina to blow itself apart could be 10,000 years, somewhere between 10,000 years to 50,000 years. And while that sounds like a long time to you, the probability of catching a star in that moment of its life is a wicked small percentage of the star's overall lifetime, because they live for tens of billions of years. So the catching a star in the act of blowing itself due to radiation pressure is statistically really, really low. When you look out at a field of stars, you're just going to see them at some normal portion of their life. So the reason why images like Eta Carina are so rare to us is because it actually happens very fast for a star's life or galaxy. To blow yourself apart in 10,000 or 50,000 years is like nothing. The problem is when I say 50,000 years, it sounds like a long time to you. You're a human being and you get bored in about 5 minutes. Okay, so keep that in mind. So I would say it's quite fast, Vladimir, if you follow my meaning. Let's go ahead and take some notes, and then we're going to kind of get into the interstellar medium, which is really I need to go with this. But I wanted you guys to start off by thinking that there are 3 general classes of star, and I want to take a note on this kind of thing.
By the way, so the larger convection zone also contributes to a darker spectrum of a star, right? No?
Okay. So yeah, well, it depends on which end of the spectrum. Let me show you a picture that will disprove you in a second. But you did remind me, Vladimir, that I forgot to give my main point. Why is the interior well, maybe you understand my point. Why do you think the interior core of this star is convective?
I have no idea, honestly.
Okay, fine.
Because
Then I
of
need
the
to explain
photon
it.
pressure?
That's right, Mateus. It's the photon pressure. In fact, fusion is going so nutty bonkers, Mateus. Fusion is proceeding so rapidly and so violently at the core of this star that this star is literally threatening to blow itself apart due to its own radiation pressure. The photons are pushing against the plasma and making the plasma particles turbulent. If this wall of convection were to grow out to the edge of the star, that star would turn into Eta Carina and blow itself apart. So these are one of the reasons that high mass stars are as large as a star can get is once you push this out to the edge, the star just disrupts under its own light pressure. Very cool stuff, actually, right? We're going to talk more about this discussion that we just had is actually kind of related to our next chapter, chapter 17, about fusions in stars. But I think before we talk about the birth of stars, it's good for you guys to have an idea that there are three basic categories of star, and we're going to do that right now, okay? Three mass, how do I want to put this? There are basically three types of star. And this is a general kind of concept. Let's make a little chart for this, okay? Okay, so we have high mass stars, what we would call intermediate mass stars, and then low mass stars. If we were to do the spectral types, actually, let's do their mass range, okay? So the mass range for a high mass star is between 8 solar masses and 100 solar masses, okay? Intermediate mass stars go from 2 to 8 solar mass units, and low mass stars can be as low as 1/10 up to, 2 solar mass units. Technically speaking, the sun is actually still a low mass star, although it's the sun kind of straddles low to intermediate mass. The colors, if you put it quite simplistically, low mass stars tend to be red, high mass stars tend to be blue, and the intermediate mass stars, they just tend to be kind of white. One last thing, the spectral types. The spectral types of these stars are O and B types. These are A and Fs. And here we have G, K, and M. So I'm going to just talk writ large about high mass stars, intermediate mass stars, and low mass stars. But I'd like you to know there's a little bit of nitty gritty to connect these two. Let's take a quick look at the Hertzsprung-Russell diagram. You should have already now learned about the Hertzsprung-Russell diagram. This is like the periodic table of elements, but for stars. I'd like to point out to you that spectral types are degenerate. And what I mean by that is you can only track the masses of spectral types as long as you're along the main sequence. The main sequence tends to be where most stars are found because they live the majority of their lives on this diagonal, okay? Notice that on the main sequence, Proxima Centauri is a low mass star, maybe 1/10 of the mass of the sun. Proxima Centauri is the very lowest mass star possible. It's also a very dim star. Stars like Rigel, which is the foot of Orion, they tend to be massive and luminous, 60 to 100 solar masses. Intermediate stars like Sirius might be 2 to 3 solar masses, and they can be a spectral type A star. But this is only for stars on the main sequence. If you start throwing in the red giants and the blue supergiants and the white dwarfs, all of this gets a little more complicated. For instance, Betelgeuse is actually a spectral type M star, but it's so massive and it's so giant in radius that we do not believe that it is a low mass star. This is at a totally different stage in its life. Mass does not correspond with spectral type so cleanly up here, okay? So usually when I say that, why did I have to tell you that? Because you'll notice that I'm pegging intermediate mass stars to A and Fs and low mass stars to GKMs, but that's only if you're on the main sequence. Wow. Can't spell. Won't spell. Okay. All right. Once you're done, I'm going to erase. Let me sip some iced tea, and then it's time to erase. I got to talk about the stuff we need for our homework today.
I missed the part. What does the OBAFGKM stand for? Oh, it's in the order. Got it.
The spectral types, right? These are spectral types. Sorry if I wasn't clear about that. This is the color, and this is our general category of star.
So what is this? Oh, beautiful and fun. Guy, girl, kiss me.
Oh boy, wait, so it's OB, fine girl, kiss me. Although some of my former students have suggested other acronyms as well. Like one was, I'm probably gonna get in trouble for this, but it was, what was it? Oh boy, a fucking gay killer monkey or something like that. They're all. So you could also use "oh boy, a fucking gay killer monkey" if you want, or the traditional one is "oh be a fine girl or guy, kiss me." But my students in the past have tried, and they have successfully entertained me. I will never forget that one. Okay.
All right. I'll go with I created my own. I do oh beautiful and fun.
What about GKM?
Well, it's the same. Guy, girl, kiss me.
Oh, okay. Well, hey, whatever gets your rocks off, just remember it. That's all I care about. Mnemonic, I've learned this over the course of my life. Mnemonic devices, the thing that we just did there is called a mnemonic device. You tell a story in your head to help you remember something. And they're very powerful memorization tools. Always use them. They make you smarter, they make your brain fun, and they help you remember things for tests. Always use mnemonic devices. They're great. All right, I need to erase, guys. Now I'm going to tell you about the gas between the stars. And this is kind of a big topic in astronomy. Sometimes they dedicate books and articles to it. Some people in astronomy just study gas, okay? That's their whole lives. And it goes by the acronym of the ISM. That's how astronomers refer to it. ISM stands for the interstellar medium. And let's give the shortest, stupidest, fastest definition that we possibly could. It's the gas and dust between the stars. But it's more than just that, because of course, the gas and the dust make the stars too. So it's kind of like the Bisquick batter that makes stars. Do you guys remember the composition of the sun? Because it's basically the same as the composition of the interstellar medium. What is it?
70% hydrogen.
Okay.
Okay. The second one is, it's either 28 or 29. I'll go with 28% helium.
Correct. Okay. What about the last 2%?
Metals, but they're not metals, but we call them that.
Yes, and the astronomer term for them is metals. But here, Vladimir, we're going to differentiate the metals, okay? 1% of the interstellar medium is in the form of metals, but these metals are in the form of atomic gas. So what that means is you have a carbon atom floating around in space. You have a nitrogen atom floating around in space. Maybe you even have the occasional water molecule or an iron atom floating around in space. The last other 1% is also metals, but these metals are in the form of solid gunk, And we refer to this solid gunk as dust. Sometimes we call it cosmic nanodust. Sorry, I've got some glare here. I got to fix that. Let me get some light on the board. That will help with the glare too. Okay. Dust doesn't mean the dust on your windowsill. Do you guys know what the dust on your windowsill is made out of?
Probably our skin cells.
Right.
Mostly.
And those skin cells are actually large. You can actually see them with your eye, and they're probably 1/10 of a millimeter to a millimeter in diameter. Just think about banging 2 chalk erasers together, and you can see dust flying everywhere, right? You can see dust particles floating in the sunlight. This dust is cosmic nanodust. It's way too small to be seen, and it's not made out of dense skin cells. It's made of carbon and bits of silicate rock and other fun stuff. I'll explain it in a bit. Dust only makes up 1% of the interstellar medium, but it's responsible for so much. And I've got to get into dust today, okay? So we sometimes call this stuff cosmic nanodust. And dust is mostly made out of 3 things. It's made out of carbon, silicates, and sometimes even bits of water. But mostly, it's made up of carbon. The dust is not the same as atomic gas because these dust particles are small, but they are technically solid grains. These are not in the same phase of atomic gas because the gas, you know, there's a difference between solids and gases, right? In outer space, there are solids and there are gases. All right, I want to talk about this at some point, and I want to talk about this at some point, but I'm going to just take a moment to zoom in on the dust because some of our homework today might be about that. Let's start with a picture, okay? Let's start with a couple of different pictures, and then we'll take notes. I think that seems to work pretty good for learning and understanding. Let's go down and take a picture of a scanning electron microscope of what we think a cosmic nanodust particle might be like. In this picture, it's only 1/10 of a micron, which means 100 nanometers across, okay? So from here to here is 100 nanometers. That means this thing is smaller than the wavelength of purple light, okay? It is solid. If you were to look at a model of it, it would mostly be carbon, little bits of graphite and silicates, and then sometimes they'll even have an ice coating to it. Remember that even though these particles are small, you could not see them with the naked eye. They are solid grains because they're in the solid phase of matter. Many, many atoms are bound together to make this up. At this point, I need to do a little fact check with you because most of you don't know a lot about chemistry. What the shit is carbon? Like, could you tell me something that was made of entirely pure carbon or is almost pure carbon? What would be made out of carbon?
Diamonds, carbon fiber.
Oh,
Diamonds is one, graphite is the other. Here's a third one that's really close. Hold on.
Wait, like carbon nanotubes?
Well, hold on. Not everyone's gonna. The carbon nanotubes we can talk about eventually, Vladimir, and they are cool.
Okay.
Here's a pic. I grabbed this. One day I was looking at a house with my dad, and there was a coal pit in the house because they actually had a coal burning stove, and they had some of this finely processed lumps of coal. This is called anthracite. And I thought about this lecture, and I grabbed anthracite because this actually looks like the shape of what a dust grain might look like, although much bigger. But coal is almost 98% carbon or something, so it's black and it's sooty. I tend to think, when I think of dust grains, I imagine coal dust or something like that. That would be a good example. Carbon is one of the most abundant elements in the universe besides hydrogen and helium. So a lot of dust grains have carbon in it. But Vladimir did know one of the two. Let's learn a new vocabulary word today. Allotropes of carbon. Weirdly, one of my favorite Wikipedia entries is the Wikipedia entry for the allotropes of carbon. What is an allotrope? An allotrope is when one substance, pure carbon, can make two totally different materials. And yes, there are some crazy ass nanotubes that we have to talk about. But let's start by looking at these two diagrams, which I think are really, really helpful. Besides the synthetic carbon stuff that Vladimir was talking about, in nature, carbon takes one of two forms: graphite, which you know is pencil lead, and diamond. And both are made of pure 100% carbon with only one difference, and that's how the atoms are arranged into molecules. In the case of graphite, the carbon atoms are arranged into these hexagonal sheets, and the hexagonal sheets stack on top of each other. And this is what makes them really good for making pencils, because as you rub the graphite along a piece of paper, you're tearing off sheets of those carbon rings, which then stain the paper and turn it black. All right. So that's what you're doing. You're rubbing the graphite along the paper and you're ripping off these hexagonal shapes. Now, if you take graphite and you compress it under the Earth's geological layers and you put a ton of rock mass on top of it, over time you can compress the carbons into a tetrahedronal shape. And then the material becomes totally different. Instead of being dark and black and sooty, it becomes sort of translucent to light. In fact, what makes real diamonds so valuable and so sparkly and gives them all these cool optical properties is just one carbon atom out of every 12,000 will be replaced by a single strontium atom. And it's that one strontium atom out of 12,000 carbon atoms, the impurities that give natural diamonds their sparkle and their luster and make them refractive properties of light so cool. It's funny that if you actually make a synthetic diamond of 100% pure carbon, it kind of looks like crap. It doesn't look as cool as the. So that's another lesson, is that the impurities make a thing beautiful, right? And that's true, by the way, with other precious gems as well. They'll have some repeating structure of atoms, and then one impurity in it will make it really cool and sparkly. The stuff that Vladimir was talking about, the carbon nanotubes, I could go on a garden path on that, but I'm going to save that for a different time. I will get back to that eventually. Okay, so when I think about carbon, I think about either graphite or I think about coal or soot or something like that. And that's probably how you should think of dust grains. I should mention that there is this very cool guy that I read about in the New York Times. He's from Norway or something, and he's actually a jazz musician, not a scientist, but he became obsessed with carbon nanodust. And he realized a cool thing that astronomers had never really thought about. He realized that if the Earth and the Sun are traveling around the galaxy every 250 million years, that the solar system should basically be plowing through an endless field of dust in the galaxy. And he realized that dust should rain down on the atmosphere of Earth every day, and that some cosmic nanodust should be able to be found in places like rooftops and things. So he went on a quest. It took him 10 years, basically going to rooftops and pond drains and any scum drain he could find, and just scooping bits of scum out and looking through it with a microscope until he could find something that he believed was extraterrestrial dust. And after 10 years of doing it, think about how crazy you have to be if this is your hobby. He found some and he photographed it with a macro lens and published a cool coffee table photo book. You can't even make this shit up. The article was called "Cosmic Dust All Over the Roof." I read this one day about a year ago, and the article just blew my damned mind. And why I want to show it to you is two reasons. One, the photographs he took are amazing. So these are nanometer scale flakes of extraterrestrial dust. Look how beautiful and cool they are. And let's see if we have other pictures here that I can show you. So here's some more. This would make a nice present. There he is. And he's a jazz musician, and he was a rock enthusiast. And there he is on a rooftop, just scraping scum into a sample bag so he can look for extraterrestrial dust. What a cool guy! How great it is to be a weirdo. Okay, so let's think about what dust does and why I'm so excited about it, or why he's so excited about it.
Wait, so he was for sure entering private property. So he would just come up to, I don't know, whoever, like receptionist at the building. Excuse me, can I go to the rooftop and scrape some dirt off your roof?
Because I'm looking for cosmic dust. He must have seemed like one of those tinfoil hat alien worshippers, you know? And in a way, it kind of is, right? So
And it's very interesting. Like he's just in a completely different world. Like a person is just busy with their workday, like receiving people, managing some stuff, and here it just comes guy and asks for extraterrestrial dust.
So Vladimir, here's the real question. Which job do you want? Do you want to be the receptionist, or do you want to be the guy scraping the cosmic dust off the roof? I know which one I want to be.
That's the choice you think you're gonna make.
Okay, anyways, there are two effects of space dust, okay? And hear me out. I'll explain this effects, and then I'll explain why it matters. There's something called reddening. Reddening happens because dust, if dust is around, say, 200 nanometers in scale, it means that the size of a dust grain is much closer to the wavelengths of purple and blue light than it is to red light. And that means that dust grains tend to sideways scatter blue photons. So what you have is the dust grains scatter blue wavelengths sideways, and the resulting starlight, which is transmitted through the cloud, becomes redder, making starlight appear redder than it is. And you guys can understand that if you change the color of a star, that's going to affect your perception of its spectral type. So this matters a lot for astronomers. The second is a more extreme version of reddening called extinction. Extinction is where basically you get such a long column of dust between you and the star that dust eventually will block all wavelengths of light. And this, of course, is what makes cool pictures of nebulae so rad to look at. So let me show you a sort of interesting picture that helps us to understand what's going on here. Back in the day, people would see photographs like this of a field of stars with a big apparent hole in the middle. And I think they called them Bok globules or dark nebulae or something like this. And they were really unsure of what they were looking at first. At first, it almost looked like a hole in the wall of stars. But then you start to notice a statistical anomaly. You begin to notice that all along the edge of the globule, you happen to find dim red stars. Now, am I supposed to believe that there's a hole in a wall of stars, and it just so happens that all along the wall in this complicated shape, all the stars are red? Or does it get you thinking that maybe this is actually a dark cloud in the foreground that has so much dust that it's blocking all the wavelengths of light here, and along the edge of the cloud where the cloud is thinnest, it's just merely reddening the stars? What do you think would happen if you looked at this nebula using an infrared telescope?
A lot more stars.
What would you see, Vladimir?
Maybe just a regular patch of sky.
You're pretty much correct. This is that same image at infrared wavelengths.
Oh, okay, a little bit.
Infrared has longer wavelengths, so you can see through the dust, and now you can see the stars that are sitting behind the foreground blob, okay? That's what's going on. Okay, now that you've learned those two things, why don't we look at another picture of space and think about why it's so cool? Here, I'm going to show you guys a picture of a part of the Eagle Nebula known as the Pillars of Creation. So basically what we're going to do is we're just going to, and I've shown you this picture before, we're going to zoom in on these long fingers. The Eagle Nebula is iconic and has a couple of different structures. This structure is called the Pillars of Creation. This structure here is called the Fairy. And there are names for all these different shapes because people have studied it and looked at it so much. Let's look up at the Pillars of Creation. Now, you know, because you just learned it in my class, that 70% of this is hydrogen and 28% is helium, right? Hydrogen and helium are completely colorless, transparent gases. You're not actually seeing the hydrogen and you're not actually seeing the helium. What makes this look so cool is the dust in it. It is the dust that's blocking wavelengths of light behind it. And that's what you're actually seeing. Every time you look at these totally dope, they call these things giant molecular clouds, you're actually looking at the dusty parts that are blocking light. That's what makes it look cool. Without
Yo,
dust,
astronomers cook up one of the most epic names. It's just Pillars of Creation. It sounds like some old mythological, absolutely like cool stuff. Like, it kind of makes me like feel chills. Like, Pillars of Creation, you know.
well,
Sounds very ominous.
let me kind of give you the short and dirty version of this, because I have a kind of long-winded story that builds up to how stars are formed, but it's kind of occurring to me that I'm going to run out of time and we're going to have to do some homework soon. Hold on, where's my, I'm just looking for my bar here. Okay, it's 111. So I want to talk, so there's a reason why they refer to these, Vladimir, as the pillars of creation. It's because these types of structures in particular are where star formation takes place. Now, I need you guys to recognize something before we get carried away here. The entire length of this structure, forgive me if I haven't told you this before, is probably more than 10 light years long. And the entire column of gas that you're seeing there probably contains 10,000 or more solar masses worth of material. So you're not going to crunch this whole thing down into stars because it's way too huge. In fact, believe it or not, guys, even if you got in a spaceship like the Millennium Falcon and then you like tried to fly through this thing in your spaceship, the density of gas is still so low over here in these pillars that you would actually not even recognize that you were surrounded by gas at all. The density of gas in the pillars is much greater than the density of gas out here in the surrounding nebula. But both of these densities are way like hundreds or millions of times lower than the density of air in this room. The only reason you can see the dust at all is because you're looking from so far away and you're seeing so many tens of thousands of solar masses worth of gas and dust that it actually starts to block light. In fact, here's a useful analogy. When I was a kid, if I played on the street and it was a foggy day, I would get kind of excited because fog is kind of cool and fun. So you'd look at a big patch of fog and you'd say, I'm going to run over there into the fog and I'm going to play in the fog. But what you discover is when you run into the patch of fog, suddenly you're not in the fog anymore. And you look back to where you were standing and the fog was over there. Have you ever had this experience? Because I know I have. You can't get to the fog. It's a question of column density. How much GIC do you have to look through before it starts blocking light? Okay. All right, let's jump ahead. I'm going to leap over some other topics and I want to get to star formation itself. It takes place. I want to just spend the rest of the day talking about those fingers. They are known as giant molecular clouds.
Wait, I still need extinction.
Oh, shit. Andy, I'm sorry. Extinction is dust blocks all wavelengths of light. Dust blocks all wavelengths of light. Sorry, Andy. Oh, I should have asked you. Okay, so let's start with this question. Where does star formation take place? It actually does not take place in any old form of hydrogen. It takes place in these very particular, and I'm going to put dense in quotation marks. It's dense compared to the rest of the interstellar medium. The interstellar medium has different parts, right? It has atomic gas and molecular gas and ionized gas. It takes place in particular dense. I'm not going to just say any types of clouds. Molecular clouds of hydrogen and helium and dust. So the helium and the dust are there, but it's really the molecular hydrogen. Now, you guys might not know this unless you took a chemistry class, but hydrogen gas left to itself, as long as the density is high enough, it will form a molecule with two hydrogens that are kind of stuck to each other. So this molecule here is known as H subscript 2. And astronomers refer to it as molecular hydrogen. You start getting the gas dense enough that the hydrogens start sticking together. All right, let's make it. Oh, I got an idea. The pillars of creation are an example of a giant molecular cloud. They sometimes call them GMCs. Slide 40. Here's another picture of a typical giant molecular cloud. I like to refer to this one as the FU Nebula, okay? I don't know what it's actually called, but I call it the FU Nebula, okay? So the FU Nebula would be a pretty typical giant molecular cloud, okay? And here's a little model. Look at the size structure of some of these. Some of them can be as long as 100 parsecs. How many light years would that be?
326.
Yeah, that's a pretty giant arsed cloud, right? And let's kind of recreate. This is from a more advanced textbook than your textbook, where they kind of get into the nitty gritty. But we're going to want some of this data here. Let's make this model and let's try to get some of these numbers down. Okay. All right. Ooh. Sorry. So typical GMC. Okay. So we'll kind of make this long finger-like structure. First, we'll put molecular gas represented by these dots. And this is basically the structure of the dense cloud itself. We're going to make this one 100 light years because that's easy to remember, okay? They probably come in all forms and shapes and sizes. I would like to point out, guys, well, I'll point that out in a second. Let's get the density of gas and the temperature, because these are things that we can measure through spectroscopy. According to my diagram here, in the regular cloud, temperatures are 1,000 particles per cubic centimeter and 10 Kelvin. And I want you guys to meditate on that for a second, okay? So usually, the number density in here is 1,000 particles per centimeter cubed. And in here, the temperature is 10 Kelvin. 10 Kelvin means this gas is 10 measly Celsius degrees above absolute zero. This gas is cold AF, as the kids like to say. Okay, but we're talking about outer space here, right? It's reasonable that gas would be super, super, super cold in outer space. How does 1,000 particles compare to the density of air in this room? Let's look up the number density of air at sea level for comparison. According to this, dry air at sea level is 0.25 times 10 to the 21. So 10 to the 20, 10 to the 19. So by comparison, let's write this down over here. Air in a room is about 10 to the power of 19 particles per cubic centimeter. I want you guys to tell me how many times less dense is this cloud than the air in this room.
Oh, like 17th order of magnitude.
That's right. Good. I was actually hoping you use order of magnitudes. 17 orders of magnitude. A 1 followed by 17 zeros. Actually, it's 16, right, Vladimir? 19 minus
Oh,
3.
my bad. Stupid.
What? Okay, so it wasn't stupid, insanely freaking huge. It was just 10 times less stupid, freaking insanely huge. Okay, so do you see what I'm saying? This stuff is really, really low dense. By the way, you guys know that we make vacuums sometimes, like in a laboratory.
Oh, so you meant to say that our vacuums is actually crappier than the clouds of gas?
The clouds of gas are many orders of magnitude lower density than the best vacuums that we can create on planet Earth. So a typical bell jar, I don't want to go too off the rails in this, but I want you to understand that even when we create what we think is a perfect vacuum, I think we can get down to like 10 million to 1 million particles per cubic centimeter. So the density of this stuff is thousands of times lower than the very best vacuums that we can create on Earth. We can't create a vacuum the same quality as outer space, okay? Particles just are, it's harder and harder and harder to pump every single gas particle out. Believe it or not, all of this gas is in a form of hydrostatic equilibrium. Someone remind the class what hydrostatic equilibrium is all about. You're supposed to know that.
So it's a state of matter when, well, not matter, of gas when the gravity that pulls in and the gas that pushes out, their forces equal to each other, so nothing happens to the structure.
Right. This structure is static and stable, otherwise we wouldn't get to take so many pictures of them. And that means, yeah, the gravity of a 100 light year long cloud of gas is going to be super, super weak. But the thermal pressure is also super weak because it's close to absolute zero. And that means this whole thing cannot collapse to form a star. It turns out, however, that buried inside, it is possible sometimes for some of the gas to develop an overdensity. And it's these clumpy, cold cores where stars can form. So let's make a star forming region. Let's create a region where the particle density is a little bit higher than average. We'll make it spherical because spheres are easy to study. And this is what they sometimes refer to as a cold core. And let's think through this really carefully for a second, okay? This is where stars are going to form, but I need to work you through this nice and slow. They refer to this as a cold core. And basically, this thing is going to create some star formation. Students, based on what you know about gases and the ideal gas law, if you increase the density of a gas, if you compress the gas, what usually happens to its temperature?
It increases.
Right. But now let's look at the numbers. Let's look at the numbers that we see in our diagram in my slideshow here. In one of these dense cloud cores, the particle density has gone up to, say, 10 to the 5 particles per cubic centimeter, but the temperature has only gone up to, say, 30 Kelvin. Let's take those notes. So here, ten to the 5, of course, is 100,000 particles per cubic centimeter. The temperature, however, has gone up to 30 Kelvin. To me, this seems to violate the ideal gas law. If pressure equals nKT, there's a relationship between number density and temperature. By what factor has my density gone up? By a factor of 100. By what factor has my temperature gone up?
Not really factored. Oh, 3.
3, right. So the density's gone up by a factor of 100, yet the temperature only goes up by a factor of 3. Doesn't that seem weird? How can you compress a gas yet keep it cold? There's only one answer to this question, and you're never going to guess what it is. How could you?
Hold on, don't say it yet.
Try to imagine what could be buried in this cloud that could help.
Ice?
Not ice.
No. Okay.
Not exactly.
The vacuum of
Not
space.
dust. I don't know. Dust.
That's it. It's
What?
the dust. Dust helps stars form. Okay, now it's time to learn about another role that dust plays. Dust, first of all, dust is kind of what helps hydrogens become molecules. And let's take a look at why. I'm going to erase up here for a second. The typical particle density inside of a cloud is so low that it's actually hard for two hydrogens to get together. They're floating around in the vacuum of space, and their interparticle separation is so great that the chances of them bumping into each other are kind of low. Introducing a dust grain as nature's cosmic tiki bar, okay? Because dust, the molecules that make up dust, kind of have a little bit of static forces, okay? So a hydrogen atom walks into a bar and it sticks to a dust grain due to some little electrostatic cling. And meanwhile, it floats around on Jabba's sail barge through the molecular cloud until another hydrogen atom through static forces sticks the dust grain. And then they see each other, and then this one kind of moves over to this bar stool, and this one moves over to that bar stool, and suddenly one hydrogen looks at the other and says, hey, what do you say we get out of here? Okay, and then they link up, and the diatomic hydrogen.
Time to insert careless whisper.
Huh?
Time to insert careless whisper.
Yes, exactly. Good choice. I actually really like that song. Yes. All right, time to insert careless whisper. I love it. I love it. In fact, I'm going to cue that up next time and play that. All right. Now, first of all, this is helping the cloud clump up a little bit. But here's the next thing. Individual hydrogen atoms and individual hydrogen molecules can't generate this much energy. But a dust grain is, even though tiny, a solid particle. And that means it is a dense solid and it can radiate as a black body. What happens is when the gas starts compressing and the temperature starts going up, you basically start to heat up the dust grain as a thermal sink. And then the dust grain shoots off long wavelength infrared photons, which then cool down the cloud. And this is the secret to star formation, because what's happening is the cloud is getting denser, but the grains are radiating away at infrared wavelengths all of the energy, and that allows gravity to keep getting the upper hand until gravity can squish the thing down and form the star. And this is how stars are born inside the hearts of giant molecular clouds.
So if the dust didn't do that, then the temperature would go up quicker and the pressure would
It would re-expand
normalize
again.
and then like
It would just
blow
expand.
apart it again.
Yeah, it would just kind of re-expand back into thermal equilibrium. The dust is what lets you beat the hydrostatic equilibrium and crush the thing down. Now, this actually raises a very important question that you guys might not be thinking about, but astronomers have. We have strong evidence by studying the leftover radiation from the Big Bang that the Big Bang could only have created hydrogen and helium gas, and no dust was present. All the dust came from subsequent epochs of star formation. So for many years, one of the outstanding problems in astronomy is how did the first generation of stars, the so-called population 3 stars, how did they form without the help of dust? We believe the answer to that question is that the first generation of stars formed from super giant clouds and formed like these epically massive O-type stars that were way bigger than a normal star, and they made a crazy amount of fusion super fast, and then Eddington Luminosity themselves apart. So there was a super fast generation of really big, fat, obnoxious stars, almost like the epoch of giants in the time before humans or something, right? And so this one wave of giant stars took place, and that created enough dust to get the subsequent generations going. So those are kind of interesting questions for a more advanced class, but something fun to think about. All right.
What is JR?
I'm sorry.
Oh, infrared. Oh, it's not J, it's I. Never mind.
Yeah, sorry, that's IR for infrared. I wanted you to know why do they have to shine it? Well, warm bodies shine at infrared wavelengths, and if they shine at visible wavelengths, the dust would block itself, right?
But the star dust is still very cold. How can it like give off infrared?
Because no matter your temperature, every black body actually glows. Like for instance, let's just consider this lump of iron here. Oh, sorry, I think I pulled a muscle in my leg. I somewhere have a lump of iron.
So unless you are at an absolute zero, you still can glow?
Yeah. In fact, this lump of iron is at room temperature. That means its temperature in Kelvin is 293 Kelvin. 293 Kelvin isn't very warm. In fact, this feels kind of cold to my hands. But this is 300 Kelvin above absolute zero. Believe it or not, this thing is giving off a small amount of infrared radiation. Is it a lot? No. In infrared goggles, it probably wouldn't look very bright, but infrared goggles are calibrated to pick up the infrared emission from a warm, glowing body, like a sniper or something, right? But if you calibrated the goggles properly, I guess it would have to be against a much colder background like dry ice. Compared to dry ice, this is giving off more infrared radiation, right? So yes, everything that's dense and solid, unless it is at absolute zero, will give off some amount of thermal radiation. All right. Before we break for homework, there's a formula that we need to use for two different problems today related to star formation. And this is what I was trying to get to, if you guys can bear with me. I'll save you the backstory, but I'll tell you that at one time, there was a famous astronomer named Sir James Jeans, and he calculated a formula, he derived a formula that would allow you to calculate the mass of a star if you knew the density of gas and the temperature inside of your cold core. And this formula is known as the Jeans mass. It's kind of a very important formula in astronomy. Introducing a formula known as the Jeans mass. It is the condition for star formation. And it's a very simple formula, but it's expressed in a strange way. The mass needed to form a star must be equal to or greater than 18 times the mass of the sun times the square root of the temperature cubed divided by the number density. I would like to point out something unusual about this formula. This is not an MKS formula. This requires particle densities to be measured in particles per cubic centimeter, okay? The temperature has to be measured in Kelvin. Obvi. I won't bother a sample problem with it because it's so simple that we'll just do 2 homework problems with it today. Okay? Super easy formula.
So the cloud has to have this property?
Here's the idea. When I first learned this formula, I was so confused by it because I didn't understand why it would be solved for mass. I always assumed if a cloud got dense enough, then it would form a star. But that misses the point because you have to derive your formulas in terms of observables. What properties of the cloud can we observe from Earth? Well, the way James Jeans went about it is he did this. He imagined a sphere of hydrogen gas. He chopped it in half, and then he calculated the gravitational attraction between the 2 halves, okay? Then he calculated the pressure that the cloud would have due to the ideal gas law. He calculated the force due to would be the pressure times the area. He equated the force of pressure to the force of gravity, rearranged the variables, and solved like so. And the idea was you could measure the temperature of the cloud, and using spectroscopy, you could measure the density of the particles. And then if you plugged them in, he could tell you how massive a star you would form if you plugged in that temperature and density. If you want, we could do a quick example with it. I'll show you how I calculate it. If we were to use these numbers down here of 10 to the 5 and 30 Kelvin, let me just show you how I would plug it in because it's so easy. So look at the formula, look at my calculator. I would do 30 Kelvin. Excuse me. Then I would cube it. So shift cube. Then I would divide it by the number density, 1 exp5. I'd hit equals. Then I would shift square root that. And to get my answer in solar mass units, I'll back multiply by 18 times 18. That would form a star 9 solar masses.
Oh, that was actually very helpful because I didn't really get. So 18 solar masses is just a constant. It doesn't change.
Yeah, 18 solar masses is what you would get if you had a temperature of like, well, I guess 1 Kelvin, or no, let's say 1,000 Kelvin and 10 particles per cubic centimeter. It's just a reference temperature, yeah. The variables the mass really depend upon are, basically what it says is this. It says if you have those conditions, you need enough matter to have 9 or more solar masses at that temperature and pressure to trigger star formation and get it to collapse. That means this is how many solar masses of matter you need to have at that density and temperature before gravity will actually win. Gravity wins at 9 solar masses and above. I know it's a little strange hearing it the first time, but you'll try some sample problems with it. Okay, that's all we got for lecture time. We have a homework today. It's homework number 8, problems from chapter 16. I'm happy to do those with the class. I will say that we have an option of 2 different problems. One is a kind of cool problem on dust grains, but it's kind of complex. Last semester, I swapped it out to make the homework a little shorter. Maybe I'll do that again. Maybe I won't. I'll have to think about it while I'm chilling during tea time, okay? So why don't we take tea break? And it's probably 1:39. At 1:55, we'll start the homework. Sound good to everyone? All right.
Yeah.
Take a break. I'll see you soon.
Oh, wait, last question.
Yeah.
So is Kelvins are MKS units, right?
Yes, they are.
Kelvins. So if you can boil down every MKS unit into 3 basic units like meters, seconds, and
Temperatures, MKS actually includes Kelvin. It
Oh,
also
so
includes
Kelvin is by itself.
Kelvin's a
Okay.
separate concept. You cannot resolve Kelvin into well, actually that's not entirely true. Temperature is
But
the
it's
average kinetic energy of the gas. So you could boil it down to joules if you did it carefully.
I see. Okay, thank you.
Yeah. The average means you have to do extra calculation. Okay, friends, we're getting back to it here with, I believe, homework number, what is it, 8? Is that what we decided? It's the chapter 16 one.
Yes.
By the way,
homework number 8.
I have to make an announcement that you probably already realized, which is I'm a wee bit behind in the grading, and I aim to fix that. Just bear with me, okay? So 53 replaced with 59. Do I still support that? 59 is the mass of a brown dwarf. I'm going to go back to 53 because you guys did binary star stuff last time. Oh, do I want to do that? Um, 53 involves more dimensional analysis. How much binary star stuff have you seen? That's what I need to know.
How much? I don't really know.
53 is a problem that involves calculating. Well, okay. I don't know if I should turn. So 53 is a problem that involves calculating the number of times a photon would hit a dust grain as it went through a molecular cloud. What I like about that problem is it's related to what we talked about today. What I don't like about the problem is that it's a little long. The other problem that we could do instead is calculating the mass of a brown dwarf using NK3. What I like about that problem is it's easy and it's related to some of the types of problems you'd be doing on the test because there'll be a lot of binary star problems on the final. Do you guys have an opinion? There's merits to both.
I could go with any, but
If you guys can't decide, I'm going to choose dust grain.
okay. I had a feeling you were gonna do that. I was gonna propose tossing a coin.
I honestly can't decide, which is why I tried to pawn it off on you guys. But we'll have other chances to try binary star problems. Let's do something weird and freaky today, okay? I really like it when the homework is related to what we talk about in class. That's what I like. So, edit. Sorry. So let's just change our, this is back, that's out. And then we'll say, so I'm going back to the original homework. I couldn't really decide. I was on a knife's edge and I needed to make a choice, so I just made that one. I hope you guys can forgive me or understand. I was open-minded to other input. Let's do it. I think we can handle it. You are a good class. Okay, let me set it up and then I want some readers, okay? So this is, most importantly, you gotta have your nomen, which is Latin for name. And this is AS1020. This is homework number 8, I believe. Chapter 16. Can you guys read me the problems again?
$50, $52, $53, $55, and $56.
Let's get to it. Chapter 16, number 50. Hit me with your best shot.
So it's light from a newborn star cluster.
Okay.
Suppose a new star cluster. Oh, do you need me to pause?
Yes, 1 sec, because I spelled cluster wrong. Okay.
Suppose a new star cluster is born with 1 O star, 10 A stars, 100 G stars, and 1000 M stars. Which stellar type dominates the light output from the cluster? What would the color of the star cluster appear to be if you observed it from a distance so great that you could not make out the individual stars?
How many G's, and was it 1,000 M's and how many G's?
So it was 1 O, 10 A, 100 G's, and 1000 M's.
By the way, something I didn't quite get to today, but this would actually be a pretty reasonable. Stars come in clusters. I don't know if I showed you that in one of the previous videos. Did I show you that, Mateus? It's kind of one of the cool things. Like when I have people come to the observatory, if there are no planets up in the sky and there are no good galaxies, I'll often just spend my time showing people star clusters because they're kind of pretty. You just see a bunch of stars together. If you were curious about whether nature likes to make little stars or big stars more often, this is sort of your answer right there. Nature tends to form a lot more low mass, little rinky-dink red stars like Proxima Centauri than it does the big fat giant blue stars like Rigel. They also live for less amounts of time too, so that's that. Why don't we make a little chart here, kind of explaining all of this.
So I remember that in order to compete the light output from one blue star, you need 1 billion M stars.
Right, we talked about that earlier. So you already kind of know what the answer is going to be, right? What's the answer going to be?
So it's blue light would dominate.
In which, and the O will also dominate the quantity of light. But let's make it formal by making a little chart together. I think that's the cool way to do this, okay? So we'll make a chart, make one just like I'm making. Sorry, guys, I got a little distracted there. A friend is coming over my house, so I have to pay attention to my phone because I'll have to buzz her in. So what we'll do is we'll have a column for 1O, 10 A's. So, well, sorry, a column. We'll have a row for 10 A's, a row for 100 G's, and a row for 1,000 M's. So this will be the spectral type, O, A, G, M. This will be the number. So 1, 10, 100, 1,000. This will be the luminosity in solar luminosity units. And the final column will be the total luminosity. So why don't you guys help me by looking, oh, sorry. I want you guys to use the HR diagram. Even though Vladimir already told us the answer, let's make it formal. Let's use the HR diagram as a tool, and let's look up the luminosities of these stars on the main sequence. Now, one thing we can be sure about is that these stars will be main sequence stars. I don't know if you know what I mean by that, Or you do know what I mean. Do you know how would I know that they're main sequence stars? How do I know they're not red giants or blue giants?
Because they're in the middle line over there.
Well, yeah, but we didn't know that from the description of the text. The trick is to focus on the newborn part. When stars are first formed, they form on the main sequence because that's where they go through their first wave of star formation, hydrogen to helium. Only after they run out of hydrogen to fuse, and when they start fusing other elements, then they move on to different parts of the HR diagram. I may have told you that before, I may not have, but it's okay. Okay, so let's use this as our tool. I'll use an arrow tool here. What do we want to choose for the luminosity of the O? You want to choose 10 to the 6 or 10 to the 5? What do you think?
5 to give others more of a shot.
What do you think, Tegan? The luminosity is on the y-axis. Your spectral type O's are here, right? So how many solar luminosity units have we got?
Is it between 30 and 60?
Oh, those numbers are the masses.
Yeah, I was like, M is mass.
M is mass, but we're looking for the luminosity, which is on the y-axis.
Okay.
So these are your luminosities right here, right?
Oh, so that would be between 10 to the 5 and 10 to the 6, right?
Yeah. Which one do you want to go with?
10 to the 6.
Yeah, bigger is better. Okay,
It's like almost there.
I agree. All right,
Okay.
so the very brightest O's are 10 to the power of 6 solar luminosities. What do you guys see for the A-type stars? Just anything to within a factor of 10, you know? I'd say 10. Let's do the G's while we know what the G's should be, right? By definition, a G-type star should be 1. And the M-type stars, I don't know. Let's pick the wimpiest ones, the 10 to the minus 3, okay? So this is 10 solar luminosity units. 1 solar luminosity unit. And 10 to the minus 3. Okay, can you guys help me compute the total luminosity of each clump? Give me the numbers. You don't need a calculator for this. Don't use a calculator, just add. Can you add 6 plus 1? Can you add, or 6 plus 0 rather? Can you add 1 plus 1? Can you add 0 plus 2? Can you do that kind of thing?
So that would just be just 10 to the 6 still?
Yep, solar luminosities. How about this guy? Do it in powers of 10, like a cool guy. Cool guys use powers of 10. Cool girls too. Cool people. Whatever kind of thing you self-identify with, that cool person would use powers of 10. So Tegan or
Is it
anyone
10
else?
squared?
10 squared. That's right. 100 is 10 squared. How about G?
Same thing?
Yep. And then the last one,
10?
careful.
10 squared? So 10
No.
squared?
All right, let's look at it this way. What is 1,000 as a power of 10? How do you express 1,000 as a power of 10?
10 cubed.
Right. So what do you get if you add the
Um.
powers 3 plus negative 3?
It would just be 0. It would be 10, right?
10 to the power of 0 is not 10, nor
Or
is it
10.
1.
Wait. 1.
1. 10 to the power of 0 is 1. Never forget that. Okay. So this was also a chance for me to just test you guys on your powers of 10 skills. That's useful practice to have, okay? Okay, so we can clearly see, just put a little sentence underneath it, okay? Actually, I'll do it up here because I don't feel like crouching down right now. Just put one little sentence at the bottom that says, the O star dominates the light of the cluster, and then write the overall color would be what? What would the overall color be?
Is it azul in Spanish?
My Spanish is a little rusty, but if that means blue, then the answer is yes. Azul. So for instance, Mateus is suggesting that past me shared with you a couple of pictures of star clusters. One of the most iconic and one that I love to show all of my friends when they come to my observatory is I love to show people the Pleiades star cluster. And there could be lots of K and M's buried in this star cluster, but you wouldn't know it because the blue stars just totally outshine and overpower all the rest of them. Do you guys remember what type of cluster this is? What do we call this type of cluster?
Oh, you meant the small clusters with blue and shiny stars versus the big clusters with lame and red stars?
Yes,
Open clusters.
that's right. It's called an open cluster. And this is something kind of cool. If you ever go down to the Frosty True Observatory with your boyfriends or girlfriends or your mom or dad, and you look through a telescope, you can be like, oh, check this out. This is an open cluster. And you can talk to the astronomer about that, and you'll seem like a cool person who knows what's going on in space, all right? My friend Scott McNeil runs the Frosty Drew Observatory down in Charlestown, and that's a really cool one to go to. They're open every Friday nights, and he has the same size telescope that I do, but in a way, way darker sky overlooking the ocean. So I'm very, very jealous of his dark sky conditions. Lots of my students have gone down in the past and hung out there on a Friday and said it's cool. I've been meaning to do that. I've got to take a trip down there one of these Fridays. By the way, if you're on, it's at Ninigret State Park in Charlestown, Rhode Island. It's open every Friday night. It's currently open even despite COVID. I think you just have to make a reservation beforehand so they keep the clumps kind of small. Anyways, let's move on to another problem. Can I erase, Andrew? Are you still here? Can I erase this? Okay, Tegan, you want to read one?
My mic was off. I don't have the questions open. I will go get them.
Okay, I'll pick someone else, but get the questions open in your browser if you're willing, and that way I can call in everyone
Yeah.
that I see.
Yeah.
Kiana, you're next. Do you want to try?
Yeah, I can read it. It's
Okay.
52, right?
Yeah, please.
Okay. It says water in molecule clouds. The water molecules now in your body were once part of a molecule cloud. Only about
I'm
what?
gonna correct you. Sorry, Kiana. It's
Am I pronouncing it wrong?
well, we say molecular clouds, so I figured
Molecular. Okay.
I'd tell you the way we say it.
No problem. Okay. Only about 1 million of the mass of the molecular, my bad,
Yeah.
cloud is the form of water.
Only,
Oh my
what did you
God.
say, 1/1,000,000th?
Yes, 1 millionth.
Wait, here's a pause. Let's ask a question while she's reading here. What would a millionth be as a power of 10? Can you guys answer that? What's a millionth expressed as a power of 10?
E 10 to the -6.
Oh yeah, exactly. Before she continues, let's write this down. And Kiana, you write this down too as an expression. They're saying to us that the mass of water is only about 1/1,000,000th of the mass of the cloud. That's how we would express this as a mathematical statement. Learning how to translate from words to math is one of the key skills that a scientifically literate person can do. So I think the words that you said was the mass of water represents only 1/1,000,000th of the total mass of the cloud, right, Kiana?
Yes.
So watch how I represent this. I'm going to draw a big old molecular cloud, and I'm putting a bunch of black dots to represent, say, the hydrogen gas. And I'm just going to put like 1 or 2 blue dots. Actually, maybe I'll make them look like little water molecules, because water is H2O. So I'll just put in a couple of water molecules in there. They look like a little thing of cherries or something, okay? All right, keep going.
Okay. Where was I?
You could start with
About.
the mass
okay.
of water being a millionth of that.
All right. The clouds form one. Okay. And the mass density of such a cloud is roughly 10 to the negative 21st gram/centimeter cubed.
Okay.
It's a
yeah.
3, just in case I said the wrong one.
This is very different, not very different. This is a little bit different than a number density. This is a mass density. They're telling you the density of the cloud in grams per cubic centimeter. Okay, keep going.
Delta is for density.
I like to use delta for density. I just don't have, I don't want to call it D because you'll think of diameter or distance. So I like to use delta for density.
All right. Estimate the volume of a piece of molecular cloud that has the same amount of water as your body. How does this volume compare with the volume of the entire Earth?
So let's say I weigh about 200 pounds, okay? How many kilograms would that be? Roughly, what do you think, Vladimir?
I think it would be roughly 91 kilograms.
Yeah, let's just go with 90 kilograms. Oh, am I made of 100% water, or what's the usual ratio that people quote? Is it 2/3 or 75%? What do you think?
I mean, the water content decreases as you age.
Right, but by a small amount. Like, we're just looking for a ballpark order of magnitude. I mean, I don't think all 90 kilograms are water. Probably about half of that is whiskey in my head, actually. So who knows? Maybe some of it's bone and other stuff. Definitely not a lot of it is brain, that's for sure. Let's see what they say here. What percentage?
Hold on. You weigh 200 pounds?
60%. 60%. Okay, so let's take 60% of that to get the real mass of the H2O. The mass of just the H2O is probably 0.6 times 90 kilograms. What would that be? What's 6 times 9 again?
54, so 5.4.
But
Wait, why did you put?
It's
Oh,
90,
point. Yeah, so, oh, okay.
so maybe 54 kilograms worth of water. Does that sound right?
Yeah.
By the way, I went with my weight, which might be around 200 pounds. One rule of thumb is that your mass is roughly half your weight. It's 2.2 pounds per kilogram or something like that, right?
Yeah.
Okay. What do we do next? Now, this is a problem where there's no formula. You just have to think your way through. I want to find the volume of a cloud such that, oh, we're missing some. Oh, they tell us that the mass of the water is 10 to the -6 times the mass of the cloud. So if we know how much water we need to have, we should know what mass of a cloud we need, correct?
Yeah, so you divide by 10 to the -6.
Which is the same as multiplying by 10 to the power of 6. So the mass of the cloud then is 10 to the 6 times the mass of the H2O. And that basically gives me 54 times 10 to the 6 kilograms. Now, we can relate the mass of the cloud to the volume of the cloud through the density, because density is also equal to mass divided by volume. Okay? So we need to convert from kilograms to grams if we want to make use of the density. How do I convert from kilograms to grams? My metric loving friends.
Is it Matthias, the converter?
Oh yeah, Matthias the converter. That's his epithet, Matthias the converter. If you were a knight, you would be Sir Matthias the converter, okay?
Come on, Vladimir. All right, dimensional analysis.
All right, let's do it. Units.
Grams on top and kilograms on the bottom.
And our conversion factor?
1,000 grams equals 1 kilogram.
Let's express it as a power of 10 like cool guys do. 10 to the 3, okay? 6 plus 3 is 9. That gives us 54 billion grams. That's the mass of the cloud. So far, so good. We got the mass of the cloud. I want to erase this little strip up here. Can I do that? All right. Thank you, Amy. So let's say that the density then, okay, wait a minute. Let's just rearrange this. If density is equal to mass divided by volume, I can flip the volume up and the density down. And I then get that the volume of my cloud is the mass divided by the density. The mass is 54 million grams. The density is 10 to the -21 grams per cubic centimeter. Can someone do that in their head like a cool guy?
54 times 10 to the 30th
Yes.
centimeters cubed.
Right, because 9 plus 21 is 30. Now, I forget I have to admit, guys, I'm not so good at names of big numbers because I have trouble with that naming scheme. So I actually have to look this up because I'm kind of.
Now that octillion is 27 zeros, but beyond that, nonillion.
Wait, are you using the British or the American version?
I don't know.
I almost put names of large Americans. Names of large. Okay, that list might be unfortunately long. So it's actually different if you do British versus the US versions. So I was wondering, you being a
Milliard, yeah.
So a non-illion is how American would say it. That would be 54 nonillion cubic centimeters. Whatever the heck that is, nonillion.
Wait, what? They use octillion for 48 zeros?
British
Okay.
and Central Europe does. So that must be, I suspect that
Hold up. How are they jumping by a factor of 1 million and not 1,000? What?
I don't, because for some reason the British have this billiard.
Oh, billiard. Oh, wow. Okay.
This is one of the many reasons why names of large numbers get confusing. But I just use this chart and look it up. So 54 nonillion centimeters. Now, their idea was, how would this compare to the volume of Earth? Because think about it. At some point, the water molecules in your body, they didn't just form out of the ground. They were once dispersed in molecular clouds. So we're trying to figure out if your body is 60% water, what volume of space was the water in your body once spread out over? 54 nonillion cubic centimeters is pretty big. It's certainly bigger than the volume of Earth. Let's see if we can calculate that real quick, okay? The volume of Earth.
Wait, so volume of a sphere is what? 4/3 pi r cubed, right?
Pi r cubed. And let's use for the radius. We know the radius of Earth is 6,400 kilometers. Watch my quick and dirty conversion. I know that there are 10 to the power of 5 centimeters per kilometer. So I'm just going to plug it into my calculator like that and cube it. Do 4 divided by 3 times pi times 6,400 exp5 and cube it and hit equals and tell me what you get. Shout at me, peoples.
27 billion cubic centimeters.
So 30 versus 60 is a factor of 2, right? Let's call that 30 and let's cheesily call that 60. The lead digit is 2. The power is, can someone confirm that for me? That sounds too low. 5, 6, 7, 8, 9. If you cube 9, 9 times 3 is 18. You fucked up.
Oh my bad. Never mind. Never mind.
That's why we all have to punch, not just.
Yeah. Just never mind that answer. You can go ahead and erase it.
1 times 10 to the 27th. Is that right?
Say that again, Mateus.
1 times 10 to the 27th.
That sounds better. Can a third person confirm this, please?
Yeah, I stopped doing crappy math and I got the same thing. Yeah.
Okay. So how many times is that versus that?
Oh, 54,000 more volume,
How many times?
right? 54,000 more time.
Wow.
How do you even say
So
it?
let's say 50,000 times more spread out than Earth, or 50 times larger. So that's.
I didn't mess up this time, right? It's like 3 zeros and then 54. Yeah, sounds right. Looks right.
Yeah, so that's 50,000 times the volume of Earth. I think at one point I calculated the radius, and it's kind of comparable to a cloud whose radius is the distance between Earth and the moon. So basically,
So much for one person, huh?
Right. Now imagine all the people in Earth, and you realize quite a bit of gas and dust have to get crunched down to make all people on Earth. Just imagine.
So can I make a claim that I am 13.8 billion years old?
In a way, the atoms, well, you can't if you consider yourself a psychological construction of matter, but the atoms in your body probably are. Actually, no. 13.6 billion years ago, the universe was mostly in the form of hydrogen. So your matter comes from a second generation star. We probably are orbiting a third generation star. So you could probably claim that most of the matter in your body is, besides the hydrogen, is, I don't know, maybe 10 billion years old or something. That's about it.
But what about the quarks? They didn't change, did they?
No, the original matter should have been a kind of quark gluon plasma. But anyways, this all starts to get semantic. Can I erase this? You know what it really is, bro? It's the energy. Your energy doesn't change. It's like one big cosmic energy. Let's smoke some weed and look at our co-star. Okay.
I mean, it didn't work because the conservation of energy matter, like energy really didn't change.
Really, it doesn't. All right, I'm erasing. I'm erasing. 52 down, and now we're on to 53. 53 is kind of the big kahuna. I was a little scared of this one. Vladimir, I'm going to have you read this one. Mateus, you read one, and Kiana read one, and now Vladimir. And then I'm going to get Amy and Tegan if I can impose on you guys. But for now, Vladimir, I want you to read 53.
So 53, interstellar dust grains. Dark. Okay.
Okay, before he reads, can we all draw a pregame picture? Let's pregame this. Let's draw a kind of quasi-spherical cloud, and let's fill it with dark black nano dust grains. You guys will remember from today's lecture, one of the reasons I wanted to do this, that dust grains are much more effective at scattering blue photons than they are red photons. The story that Vladimir is about to read is of a little blue photon traveling through the cloud, and we're trying to figure out how often it'll hit a dust grain. So let's draw our little blue photon coming in. It's going to hit the dust grain, and then it's going to scatter off to the side, okay? Okay, Vladimir, read it away.
So, dark interstellar gas clouds contain so many dust grains that starlight cannot pass through, even though the dust grains are tiny and the spaces between them are quite large by earthly standards. A typical dust grain has a radius of about 10 to the negative 7 meters and a mass of about 10 to the negative 14 grams. Estimate how many dust particles there are in a cloud containing 1,000 solar masses of dusty gas if 1% of the cloud's mass is in the form of dust grains.
Okay, I've taken the words that he spoke and I've put them into a kind of math format. Let us call the number of grains capital N. Notice for a single grain, I used lowercase r and lowercase m to try not to be confusing. So here's a little grain. A grain has a radius lowercase r and lowercase m. The mass of the entire cloud is 1,000 solar masses. The mass of the grains is 1% the mass of the cloud. If in part A, our goal is to find the number of grains, do you guys have any idea how to do that?
Find the mass of the clouds.
The mass of the cloud is known. It's 1,000 solar mass units.
So just take 1% of that.
Yeah, that'll give us the mass of the grains. And then here's my logic, Mateus, see if you can follow me. If the mass of the grains is like a big number, and each individual grain is like that, we'll divide the total mass by the mass of the individual grains, and that will tell us the mass of one grain. That'll tell us the number, right? Like if the total mass of the grains was 12 kilograms, and each grain was 1 kilogram, we'd have 12 grains, right? Something like that. Okay. All right, so let's do that. So let's say that the mass of the grains is 1% is 0.01 times 1,000 solar masses. You can do that in your head probably, right? What do you get?
10 solar masses.
Okay, I'm going to do us a quick favor to speed this problem up because it's kind of long. The mass of the sun is 10 is 2 times 10 to the 33 grams. I'm basically converting it into grams for you just to save a little bit of time. So let's do 10 times. If the mass of the sun is 2 times 10 to the 30 kilograms, it's 2 times 10 to the 33 grams. And that means the mass of all the grains is 10 times that. 2 times 10 to the 34 grams. That means that the total number of grains is the mass of every grain divided by the mass of a single grain, which is 2 times 10 to the 34 grams over 10 to the minus 14 grams. Someone do that in their head like a cool person.
2 times 10 to the 20th.
Perfect.
Maybe 48.
Oh, sorry. Yeah, Mateus, 34 plus 14 gives you 8 and 4, 48, right?
Oh, it goes back up positive. That's right.
Right, because if you divide by a negative, you add the powers again, okay? So 2 times 10 to the 48 grains, where grains is kind of a dummy unit. That's a lot of dust grains, if you think about it. Guys, get that down. Let me get a cup of iced tea, and then we'll proceed. All right. I'm going to erase. Everyone cool with that?
Yeah.
Let's get part B going.
So the part B goes as follows. Estimate the total surface area these grains would cover if you put them side by side. You can assume that the grains are approximately spherical, so each grain covers area of pi r squared, where r is the grain's radius. State your answer in square light years.
Okay. Let's imagine that we make some dust chainmail. So we take all the dust grains, and just like a hauberk that a knight would wear, we make some chainmail by linking all of those dust grains together. Is that what they call it, a hauberk? How do you say that? You got to know what the F I'm talking about, right? Come on, you D&D playing geeks out there. I know you exist. I know you've been to King Richard's Fair. What is it called? A hauberk. Something like that. Okay. Ooh, that one's a little risque. I don't know if I want to look at that one during class time. All right, so let's look at it later though. All right, so, all right, here, yeah, hauberk. We're making some, there we go. So you're making some chainmail, right? This is what I think of when I think of a hauberk, right? And we're putting all those dust grains side by side. I happen to know that if we, the surface area of a grain is 4 pi r squared. Sorry. The surface area of a sphere is 4 pi r squared. But a photon doesn't see the full three-dimensionality of a sphere. It basically sees a little disk or a target. And I remember from my basic geometry class that the area of a disk is pi times the radius squared, okay? That's the area of a target, like a bow and arrow target. So my guess is that the total surface area would be the total number of grains times the area of each little grain as a disk, which would be n times pi times the little radius squared. And I think they told us in the problem that they want this eventually in square light years. So we'll get to that. So the number that we had for the number of grains was 2 times 10 to the 48. I'm not going to put a unit here because grains is like a dummy unit, times pi times the radius 10 to the minus 7 meters squared. Here, I want you guys to be super, super careful about how you do this. Punch it into your calculator or do it in your head if you think you can. What's 7 times 2?
14.
14.
So that, and pi is about 3. 3
That would go
times
back to
10 to the 14.
24.
3 times 2 is 6. What is 6 minus 14? Oh, sorry. 6, what is 48 minus 14?
34.
So you get approximately, if you guys followed my logic, 6 times 10 to the 34 meters squared. Did everyone follow that? I imagine that pi is the same thing as 3, because who cares about 1415926, right? So 3
Yeah, for
times
example.
3 times 10 to the negative 14. 3 times 2 is 6. 48 minus 14 is 34, according to Vladimir. I hope you're right about that. Okay, you are. All right, now let's convert it to square light years. Watch this slick Rick maneuver. Do you guys remember what I gave you a couple of weeks ago as the conversion from meters to light years?
Yeah, but you have to square it, right?
We have to square the conversion as well, but first let's just do 1 light year is how many meters?
Oh, 9.5 times 10 to the 15th.
Very good. Good memory, son. Now, that means if we want to go from light years to square, we have to square everything. Square light years, square meters, square 1, and then you have to square 9.5 times 10 to the 15. I think I'll just do this one out here. So 6e34, woo, 6e34 divided by 9.5 exp15, then I'm going to square that, badoop, and then equals, gives me about 665 or maybe 700, let's just call it 700 square light years, because we're just trying to get a rough ballpark idea. That's the answer to B. When you have that down, I'm ready to go. Oh, sorry. I'm stretching my leg because I hurt my hip doing something funky and I don't know what it was. Or my leg, or some part of my body is hurting and I'm afraid it's just me being old. Okay, can I erase this? I'm doing it. Okay, what's part C ask?
Estimate the total surface area the cloud covers, assuming that its matter density is like that of a typical molecular cloud, about 10 to the negative 21st grams per centimeter squared. Cubed, my bad.
Centimeter cube, right?
Brain fart. Hint.
Oh,
First, without the hints.
no, let's get that hint. We need that hint.
And first, calculate the cloud's volume from its mass and density. Then determine the cloud's radius using the formula for the radius of a sphere. R equals 3 times the volume divided by pi by 4 pi, and everything to the 1/3 power.
If you reverse the volume of a sphere 4/3 pi r cubed, that's a cube root, right?
Yeah, it's a cube root.
So it's the cube root of 3 times the volume over 4 pi. Okay. First,
So
define the volume of a cloud.
years.
From our previous problem, the volume of a cloud is its mass divided by its density. And I believe they said the mass of this cloud was 1,000 solar mass units. Was that correct?
From part A, yes.
So remember that 1,000, and I gave you the mass of the sun as 2 times 10 to the 33 grams divided by 10 to the minus 21 grams per centimeter cubed. Let's see if we can cool guy this, okay? 33 plus 3 plus 21. What do you get? 36, 57? 2 times 10 to the 57, is that right? You guys see how I did that? (33 plus 10 to the 3 plus 10 to the 21). What are my units?
Cubic centimeters.
Okay. Now let's calculate the radius of the cloud.
So we're just assuming that it's spherical.
Yeah. There's a funny joke in physics about this, okay? And it goes like this. A bunch of farmers have these cows, and the cows aren't producing enough milk. There's something wrong with them. So they hire a team of physicists to analyze the cows and figure out what the problem is. The physicists work it out, and they bring the farmers into the boardroom to try to explain to them the problem. They sit them in front of the dry erase board, and the physicists say to the farmers, "Picture a spherical cow." And that's the joke, okay? The joke that only physicists laugh at, if they even do at all, is that when physicists have to model complex problems, they just assume they're a sphere because you always know the surface area and the volume of a sphere. The reality would be actually too complicated to model, so let's just assume the cow is a sphere. But if you're a farmer and someone says, picture a spherical cow, that's not actually going to relate to the cows that they know. But to a physicist, maybe it's about the same thing, okay? So picture
It's talking about topology.
Yes. Now, is my cloud going to actually look like a sphere based on what we've seen today? Probably not. But who cares? We'll probably get a close enough answer to be good. Okay, so let's calculate the radius of this spherical cloud. And let's do it by doing 3 times 2 times 10 to the 57 centimeters cubed, all divided by 4 times pi. Can you guys handle that for me without mistakes?
Is it 8 times 10 to the 18th?
Sounds plausible. Sounds very plausible. Let me fact check you. Yes. And units?
Centimeters cubed?
No, because we took the cube root of centimeters cubed, didn't
That's right.
we? So it's just centimeters. Let's now convert that by doing 100 centimeters per meter on the bottom, and then meters to light years is 9.5 times 10 to the 15. Can you guys tell me how many light years that is?
So 8.4 light years.
Now that's the radius of the cloud, right? Now, the total question, if you remember back to the question, it wants to know how does the photon see the surface area of the cloud? If a photon is looking at the cloud as a target, the cloud is actually a giant disk whose surface area is pi times the big radius squared. So the surface area of the cloud, if it's like a bow and arrow target, it should be pi big R squared. So at the end, I'm going to erase this bit here. The total surface area of the cloud will be pi times 8.4 light years squared. What do you get? Just 1 sig fig is fine.
$70 pi light years squared.
Huh?
No, I was too lazy to multiply by pi, so it was like 70 pi light years squared. So it's
64 times
200.
200 square light years. Hey, Vladimir, thought question for you. We found that the total area of the grains was 700 light years, but the total area of the cloud is less, 200 square light years. Vladimir, how can the total area of all the grains be greater than the cloud that encompasses them?
Because grains are much bigger than the than the atoms in the cloud.
No. The grains are, you're still missing the point. The cloud is a large enough volume to contain the grains and then more. But how is the surface area of the grains greater than the cloud? Because you're pushing the forward and backwards grains all up against a wall, all in one big Hauberk sheet, in a chainmail sheet, right? So smushing all those grains forwards and backwards, you actually get more total target surface area of grains than you do clouds, which is kind of wild.
So there are what? There are more grains than molecules? No.
Okay, no. The cloud contains 70% hydrogen, 28% helium, and 2% is either in the form of wacky atoms floating around. 1% is in the form of wacky atoms, 1% is in the form of grains. So the cloud is much greater than all the grains. There's a lot more stuff than just the grains. The grains are interspersed, but even still, the total surface area of all the grains exceeds the surface area of the cloud as a target, which is a weird thing to think about. Let's just read part D and be done with this problem.
Based on your answer to parts B and C, what do you think the chances are that a photon passing through the cloud will hit a dust grain?
So let's make a sort of crude argument here. If you have a dartboard, if the area of your bullseye is half the area of the dartboard, you've got a 50% chance of hitting it if you throw a random dart, right? So I would say that the percent chance of a photon hitting the dust grain is the area of all the grains divided by the area of all the cloud as a disk. But the area of the grains is greater than the cloud. 7 divided by 2 is 3.5. What is that as a percentage?
350%.
What is the meaning of the 350%?
You are 3.5 times more likely to hit a dust grain.
A grain, or in other words, if you're 3.5 times more likely than hitting one dust grain, you're probably going to hit 3 to 4 dust grains on your journey through the cloud. So the photon will hit somewhere between 3 and 4 grains on its journey through the cloud. You want to know what tells me? That tells me why the Pleiades have that cool ass blue color around them. Where'd my Pleiades go? Did I look at the Hauberg from? Where's my? Oh man, there we go. Do you guys see all that cool blue crap surrounding the stars? That's the problem we just did. Those are the blue photons leaving the star in like this direction, hitting a dust grain, and then scattering towards the camera. And you can see just from the dust grains all of that cool blue stuff surrounding the Pleiades. Pretty neat, right? This is why reflection nebulae are so blue and so beautiful. Reflection nebulae, as we call them, this is an open cluster, but if you type in the word reflection nebulae, it's because the dust grains are reflecting blue light. There are hundreds of different examples of reflection nebula. One that I like to show students around Halloween time is the legendary Witch Nebula, which has blue photons scattering off dust grains in the form of a creepy witch. But there are many other beautiful reflection nebulae. Anytime you see cool blue gas in space, that's a reflection nebula, okay? There's hundreds of pictures.
Wow, look at that Xbox Reflection Nebula.
Yeah, maybe that's where they got their logo. Who knows? All right, cool. We got through the hard problems. The other problems today are wicked simple. Amy, we haven't heard from you in a while. Would you be willing to read us a problem?
Yeah.
Thank you. Amy, I task you with reading number 55, if you're willing. Can I erase this, everyone? I kind of was standing in the way.
I'll take a screenshot of it really quick so you
If
can just erase it.
Okay, sure. Whatever you got to do.
All right, all set.
All right, I'm erasing. Okay, 55.
Masses of the first stars. Models of the first star-forming clouds indicate that they had a temperature of roughly 200 K and a particle density of roughly 300,000 particles per cubic centimeter. At the time they started trapping their internal thermal energy. Estimate the mass of which thermal pressure balances gravity for these values of pressure and temperature.
So we need to know the mass of star needed to overcome pressure, to overcome the gas pressure. Do you guys remember we learned this formula today? What mass of star do I need to overcome the gas pressure and compress into a star?
Oh, is it NKT?
No.
No?
This is the gene's mass, right?
Oh, that. Oh, so it's 18 solar masses times the square root of I forgot.
T cubed over the number density. And we already have the right units, so we just have to plug it in. That's all we have to do. Why don't you guys try to do that based on how I showed you today? See if you can get that.
93 solar masses. Does that sound plausible?
Yep. What type of spectral type would that be?
Ooh, that would be like borderline blowing yourself apart. So, oh,
Exactly. So they believe those first generation of stars were like super O stars, really, really high mass O stars. And like I said, they would have blown themselves apart super fast. And they would have a very short time. Did they ask how long they would live?
Yeah, I did.
If you guys remember, the lifetimes of stars are also printed along the main sequence.
10 to the 7th.
But that's, yeah. So
Oh, that's the main sequence.
yeah, no, that's good though. Main sequence is when they form. So yeah, these stars would be less than 10 to the 7 years or 10 million years. So they would have a lifetime.
Probably like 1 million years or something.
Yeah, it's hard to know exactly how it is. 1 million sounds short. Let's just say less than 10 million years. Maybe a million, yeah, maybe a million years, Vladimir, maybe. Wow, I think Siri was just trying to answer that question because I hit the button.
So what is the threshold for a star to explode, pretty much?
The famous astronomer Stanley Arthur Eddington, who did many different cool things during his career, he was famous for having derived the Eddington luminosity. And I think when you calculate it out, it comes out super close to 100 solar mass units. The Eddington luminosity is usually something you'd learn about as an actual astronomy major student. It's usually not for 101. But I like to sprinkle that stuff in because I kind of think it's cool. The actual calculation's a wee bit over the cost of this class, but it looks like his calculation shows that it's 30,000 solar luminosities for every mass over the mass of the sun. And let me see if I can translate that into English for you, okay? This number, 3.2 times 10 to the 4, is 32,000. And what that means to me is if our sun was going to achieve its Eddington limit at one solar mass, 32,000 solar luminosities would blow our sun apart, okay? For a mass of 100 solar masses, you would need 3 million solar luminosities. Considering that an O star is already at 1 million solar luminosities, an O star is dangerously close, 33% away from blowing itself apart. So that probably would blow its lifetime would be really short because it would crunch through its fuel fast. But this star is very, very close to the Eddington luminosity. Once you get to 200 solar masses, you've already exceeded your Eddington luminosity because you're like at billions, or you're just so your luminosity starts to match your Eddington luminosity, something like that. Okay, did that make any sense? I don't know if that made sense to you guys. It made sense to me. Okay, cool. All right, great. This problem is done. Let's move on. And Tegan, you will be our last reader if you're willing.
Hi. Okay.
Can I erase everyone? Any objections to me erasing? This is going to be another variation on the problem we just did.
Okay. Says internal temperature of the sun. The sun is essentially a gas cloud in which the forces of pressure and gravity balance each other. We can therefore use the equation in mathematical insight to estimate the interior temperature of the sun from its mass and particle density.
Okay, let me just pause you right there, Tegan, before you go on. The formula that they're referring to is once again the Jeans mass, but today we're going to use it for a bastardized version to do something tricky. The Jeans mass tells us that the mass of a star in thermal equilibrium is about 18 times the mass of the sun times the square root of T cubed over the number density. Let's make the following argument together. The sun is in hydrostatic equilibrium. That means the forces of gravity pulling in are equal and equivalent to the forces of thermal pressure pushing out from the center of the star. Therefore, we can assume that the sun is in sort of thermal pressure balance. We're going to make this an actual equal sign, and we're going to use this intel to calculate the internal temperature of the core of the sun. But to do that, we're going to have to figure out the temperature, the number density there. So go ahead, Tegan, and keep reading the problem.
Okay. A says, what is the average number density of particles within the sun, given that the average mass per particle is about 10 to the negative 24th grams?
Okay.
It says hint.
Atom. Let's assume the sun is made 100% hydrogen for simplicity's sake. The mass of a hydrogen atom is 10 to the minus 24 grams. I know that the number density is the total number of hydrogen atoms divided by the volume of the sun. And since I know the radius of the sun, that should be pretty easy. It'll be the number of atoms divided by 4/3 pi times the radius of the sun cubed. Do they ask us to find the number of, I thought part A asked us to find the number of atoms in the sun. Is that what happened, or?
It asks for,
I mean, you must have read it right. I can't imagine you would have read it wrong.
yeah, this is the average number density of particles within the sun.
So this might have been confusing to do without my help. The number density is the number of atoms per volume. I know the volume of the sun. I need to figure out the number of atoms in the sun. One way to do the number of atoms in the sun is to take the mass of the sun and divide it by the mass of hydrogen atoms. The mass of the sun is 2 times 10 to the 33 grams. The mass of a hydrogen atom is 10 to the negative 24 grams. If we do this cool guy style, 30 plus 20 is 50, 3 plus 4 is 7. Once again, we have 2 times 10 to the 57 atoms in the sun. Now I'm going to use this to get the number density by dividing it by the radius of the sun. By the way, for the record, the radius of the sun is 700,000 kilometers. If we multiply that by 10 to the 5 centimeters per kilometer, we get 5, 6, 7, 8, 9, 10. The radius of the sun is 7 times 10 to the 10 centimeters, okay? I'm just doing some of the conversions quickly, because if I make you guys do every single conversion, we're going to be here so long that I'll starve to death, all right? So I'm just cheating a little bit for the sake of time. I'm doing some of these conversions on my own. All right, so let's calculate the number density. The number density is the number of atoms, 2 times 10 to the, 57, divided by, actually, I'm going to flip the 3 up here for mathematical sake, times 3, divided by 4, divided by pi, And the radius of the sun is 7 times 10 to the 10 centimeters cubed. Can you guys calculate that for me? I don't know if you can see that clearly or not. Can you guys read that okay? It's not awesome, I know.
Oh yeah, I can see it. Yeah.
All right, cool. All right, so punch that up for me, kids.
One 1.4 times 10 to the 24th. Did anybody else get something else?
Same.
Hold on, guys.
So the units are atoms per, well, particles per cubic centimeters.
Remember that particles are kind of, what was the number again? Sorry, I had to open the door for my friend. What was the number?
Mateus? Okay.
Anyone?
You could have said
One-
it.
Yeah, but like professor wasn't here. 1.4 times 10 to the 24th. Wait, by the way, Mateus, did you get a haircut or something, or
I
they
did.
just-
I cut
Oh,
most
wow.
of my hair off.
Yeah,
No,
I remember that being very long.
It looked like you cut it. I was
Yeah,
thinking
Yeah, I
about
couldn't
that.
tell if he put it back in a ponytail or not.
Yeah, the whole lecture I was wondering.
I'm glad we could resolve some of the other fundamental mysteries of the universe, like what's going on under Mateus's baseball cap. Anyways, actually, Mateus has been with me. This is the second class. Oh, wow. You cut it real short, buddy.
Wait,
So I'm used to all these videos of seeing Mateus with longer hair, but still,
I can see it. Hold on.
oh my gosh. Oh my gosh. All right, wait. So Mateus's hair aside, let's get the units of this so that I can eat a sandwich or something. Make yourself at home. I'm almost done. Atoms per cubic centimeter is one way to look at it. Remember that atoms are kind of a conceptual dummy unit. So the real units of number density are 1 over centimeters to the power of 3, which is the same thing as saying centimeters to the minus 3, okay? You can, in your mind, imagine the units being particles per cubic centimeter or atoms per cubic centimeter, but it's really centimeters to the minus 3, which is a little bit goofy. Okay, boom. We got the number density. Everyone get that down. And then Tegan, I want you to read us part B.
Okay. Part B says, what is the approximate temperature necessary for gas pressure to balance gravity within the sun, given the average particle density from part A?
Okay, do you guys have this all down? I'm going to have to erase. See if y'all can follow my sweet algebraic moves. Let's assume that the sun is in a thermal equilibrium balance where the total mass of the sun is balanced by its gas pressure, just as James Jeans imagined. Then I could say this mass is actually one solar mass, the mass of the sun, correct? So for part B, I'm going to divide the solar mass units out, and I get 1 equals 18 times the square root of t cubed over the number density. Let's drop the 18 over to this side. Let's square both sides so that we get rid of the square root. That's equal to t cubed over the number density. Then I'll flip the number density up. Oh, sorry, we want the temperature. I'll flip the number density up, and I'll get t cubed is equal to the number density times 1 over 18 squared, because 1 squared is just 1. And t should be the cube root of the number density divided by 18 squared. In our previous problem, we discovered that the number density is 1.4. Was it 10 to the 24 particles per cubic centimeter?
Yeah.
Go ahead and punch that into your calculus. What's in the bag, Buster? No kidding. That smells so good. Are we going to share this? Or are you going to eat it? Okay. Okay. What'd you guys get? Sorry, we're fighting over scraps of food here.
6.6 times 10 to the 10th.
And
Is that the
no.
reason? No, it doesn't.
All right, somebody somewhere screwed up, and I want to know who.
Is anybody else having lagging issues with the?
You're lagging.
Yeah.
Me?
No,
Mr.
Matthias
Hicks.
is.
Oh.
Wait, so what did you get, Professor? Oh, it's cube root. Oh, no wonder then.
Did anyone else get something different? I got this.
Yeah, it's what is this? 160 millions. Wait, 160 millions? No?
No. Count better. Count your decimal points better. You're all failing me here. My disappointment levels are high. Yeah, as Melania says, be best, okay?
Oh, okay, 16 millions.
Yes. All right, little fishy stuff. I just got a bite of mac and cheese delivered right to my personal mouth. 16 million Kelvin, okay? Is that a random number or does that remind you of something?
It's about the temperature at the core of the sun.
Right, the temperature for hydrogen fusion is 15 million Kelvin, right? So we can figure just by assuming the sun is in a pressure equilibrium balance, we are wicked freaking close to the temperature of hydrogen fusion, proving that the sun has enough mass to fuse hydrogen, which is totally dope. Was there a part C, Tegan, or not?
I think so. It says, how does your estimate compare with the internal core temperature of the sun?
Okay, so let's write this down. For part C, say 16 million Kelvin is wicked close to the hydrogen fusion temperature of 15 million Kelvin, the core of the sun. 16/15ths. What is 16/15ths as a fraction anyways? 16/15ths is 1.07 or 7% higher than the sun's core temp. So in other words, if you need to be around 15 million Kelvin to fuse, you can prove that the sun is capable of doing self-sustaining fusion or hydrogen fusion just by assuming gravity is balancing it. Oh, yeah. What is this? That's pretty good. That's pretty good. You know, their burgers are really good too. Yeah. We're going to eat some Bucktown chicken. And let me tell you guys, you're missing out on this party, okay? All right. Okay.
So I have a question. It's kind of weird, but I looked up hydrogen fusion. It was 100 million kelvins, not 15 million kelvins.
That's probably in a terrestrial tokamak or something. Actually, kind of interesting story about the Russians in fusion, Vladimir. Obviously, if we could do fusion like the sun does on Earth, we would instantaneously solve our energy crisis and our pollution crisis in one fell stroke. What you would do is you would take seawater, you would use electrolysis to pluck the hydrogens off the oxygens, and you'd have crap loads and crap loads of hydrogen. Then you'd heat it up into a plasma. You'd heat it up in your little Mr. Fusion reactor, and when you brought it up to 15 million Kelvin, or in a terrestrial vacuum, maybe it's a bit higher. You'd have to get it to like 100 million Kelvin or something. And the Russians kind of beat the Americans at first in trying to do this. They invented this device called the tokamak. The tokamak is a giant cylindrical donut with wires wrapped around it, and you put hydrogen plasma in it, and you try to, let's see if we can find a picture of a tokamak. Sometimes you can find one with like a technician inside it for scale. But this is a giant cylindrical donut. Now, why do you need this giant cylindrical donut? You need a magnetic field to confine the plasma, because you can't let the plasma touch the walls of the container because they're much cooler than 15 million Kelvin. If the plasma touches the walls, they'll cool down and your fusion stops. So you use a hugely powerful magnetic field. This donut is basically a huge solenoid, and the huge solenoid is basically trying to trap the plasma in it. But what would happen is tiny inhomogeneities in the magnetic field would allow plasma to leak out to the walls and cool down. So they started building a tokamak in Princeton, New Jersey, and it was costing so much energy to heat up the walls of the plasma that the lights in Princeton, New Jersey were dimming down. And then like the whole city was getting pissed off. And then the politicians were like, what the hell's the point of this stupid thing anyways? And we're cutting the funding for it because it was getting too expensive. And then people decided, okay, well, tokamaks aren't the solution to fusion power. Today, we have a new method that they're working on in France that we believe has a stronger possibility of succeeding. It's known as the NOVA Laser Fusion Project. And what they do is they take a little pellet of deuterium or tritium or something, and they take this huge bank of wicked high powerful lasers, and they focus all of the lasers on a little pellet of either deuterium or tritium or something, and they try to see if they can fuse it into helium. From what I understand, a few years ago, they had an article in the BBC saying that the NOVA Laser Fusion Project had hit a critical technical milestone called the break-even point. That's where they were getting enough joules out of the system equal to the joules they were putting in. So they'd have to really turn up the electricity to power these lasers, but they were getting an equal amount of energy out. They had hit the break-even point. Obviously, to actually generate useful power, you need to get out more energy than you put in through fusion. But they consider that if you can get to the break-even point, it's just a matter of time before you figure out the rest of it. I'm hoping that in our future, instead of having a boiler in our basement, we'll have a little Mr. Fusion reactor, and we'll just pour water into it right out of our faucets, and then Mr. Fusion will separate the hydrogens and, you know, somehow fuse this thing with lasers, and then we'll get free Nintendo for life, and that would be freaking cool. Okay.
Does the water have to be very pure?
Huh?
Because does the water have to be very pure?
Maybe, yeah. I'm sure there's going to be a few other
Like,
details.
you know, tap water is nowhere near.
All right, yeah, okay, fine, okay. Maybe you'll have to go down to your local pickup truck for a distilled water. Yeah, okay, but the point is, wouldn't it be nice to not put carbon dioxide into the air and kill all the squirrels and the bunnies and make the polar bears fall through the sea ice? That would be a beautiful world that we would live in, where the polar bears could run free, okay? So, like, this is the idea. And we will get there, hopefully someday. One day we will learn how to be as smart as a star. I hope you enjoyed another day of astronomy with me, and please come and participate live next Tuesday so I don't get the day off of work, okay? It's very easy for me to give you a pre-recording lecture. Don't let me off the hook. I will participate with you if you will participate with me, okay? So turn in those homeworks. Don't forget to keep up. Right now, I've left a couple, since I've been late on grading because I've been having too much fun, I've left those homeworks and labs open from the last couple of weeks because fair is fair. but at some point I'm going to catch up. Maybe today, I'll catch up in my grading. So try to get those older things in if you haven't done it. Okay. All right, guys, I'll see you on, Tuesday. We're going to start one of my favorite subjects in all of physics and astronomy. We're going to
General relativity.
We're going to take a break from stars. We're going to do special relativity and general relativity. This is going to be a really magical week, so please tune in, okay?
Hey, let's go, finally. Check your email. I believe I sent you an email.
I will do. Okay.
some time
Over and
ago.
out,
All
guys.
right.
I'll see you later. Bye.